Earlier in the course, I talked about transactions and the acid test, and it's time to cover a little bit more about them. If you need to refresh your memory, take a look at that earlier section where I talk about the characteristics of a transaction, because here I'm going to focus just on one part, the idea of isolation. The idea that when simultaneous users are interacting with the database at the same time, how do we stop them from treading on each other's toes? This is the inherent problem of concurrency, of concurrent users. Well, first, let's understand how they might conflict with each other. Here's an example. We own a small bank, and we've got Alice and Bob, who are two customers in our system, and they have three accounts, a joint account and a separate account each for incidentals. And these are each a different row in this account table, about as simple as I could possibly make it here. And every so often, Alice and Bob want to transfer money from their joint account into the individual one. Every time they do, the process goes something like this. I'm going to assume that Alice is doing this transaction. Now I'm just going to write pseudocode here because it's not the SQL I want to talk about, it's the steps. We get the balance of the joint account. So we reach into the table, okay, joint is 10,000. We'll then get balance of Alice's account, which is 50. Then we'll perform an operation to update the balance of the joint account to what I just retrieved, which was 10,000 minus 1,000. So we're reaching into the database, setting it to 9,000, and then we'll reach back in and update the balance of Alice's account to 1,050. All well and good. We've subtracted 1,000 from joint, we've added 1,000 to Alice. And then one day, they both log on to the website at the same time and both attempt to do this move. Alice starts her operation. She reads the balance of the joint account, it's 10,000. Bob starts his. He reads the balance of the joint account. It's also 10,000. No changes have happened yet. Alice gets her balance, which is 50. Bob gets his, which is 45. Then Alice issues the update to joint. She'd retrieved it as 10,000. She'll subtract 1,000 from that, which is 9,000. She changes the database. And Bob also tries to perform that operation. He believes that joint account is 10,000, so he will also set that to 9,000. Then Alice updates her account, adding 1,000 to it. Bob updates his, adding 1,000 to that. Now the end result is that the joint account is down 1,000, but both Alice and Bob's account have been credited 1,000 each. The balance should be 8,000, not 9,000. Now Alice and Bob might be perfectly happy with this, but our little bank will stay little if we don't take care of this situation. Now, this is what's often called a race condition. It's a conflict where two people or two programming threads are doing very similar steps and just getting a little bit ahead of each other. They're trying to affect the same data. And when they're doing it together, you'll end up with a very different outcome to what would have happened if they'd done exactly the same steps, but Alice did all hers first and then Bob did his. So, the first step to fixing this situation is we make these atomic. We're making these several actions grouped into one indivisible unit by making them transactions. And we do this by adding SQL keywords at the start and end. So in this case, we use the words begin transaction. We'll do all the operations we want to do, and then we write the SQL keyword commit to say our transaction is done. Now, these are SQL keywords that deal with transactions, although you will find that you write slightly different code to create a transaction in the different database management systems. Sometimes it's just begin, sometimes it's begin work, sometimes it's begin transaction or start transaction, but again, it's the core concept we're going for here. We're starting a unit of work. We want to go all the way through and commit if everything's successful. And if there's a problem anywhere in the transaction, we want the database to roll back to the start of the transaction as if no part of it had ever happened. And I said this is step one because this by itself may not help our race condition problem if both of these transactions are still executing at exactly the same time and they're allowed to do that, because we didn't actually have any errors occur. The issue is that Bob is being allowed to read from the same table that Alice is in the process of changing, but she hasn't finished changing it yet. This is often what's referred to as a dirty read. There's a transaction going on that's partway through. It's going to be changing this data, but we're allowed to read from somewhere in the middle of that transaction. So often what happens is we don't want to just treat these all as one unit. Just making them transaction is not good enough. We also want some kind of locking to occur so that we are prevented from simultaneously changing the same data, at least until the transaction is over. Now, one way of doing this is what's referred to as pessimistic locking, where we are pessimistic that transactions will conflict with each other. So as soon as a transaction starts, we're going to lock the data that it's referring to and only unlock it once the transaction commits. So here's how this would work. Going back to the beginning situation, we're creating transactions for both Alice and Bob. So Alice's transaction starts. She reads the balance of the joint account and she will lock that information. Now Bob would then attempt to read in his transaction, but he won't be allowed to. He'll be refused. The database might return an error, but more typically, we just use blocking. We're not returning anything. We're just making Bob wait, because hopefully the entire transaction on the left is going to take 1/10 of a second. We'll commit and everything unlocks. If it's more complex, if we've got multiple updates, full table scans, the database is slow and not indexed well, Bob may end up waiting for a lot longer, or the database might return an error, or the application that Bob is using to access the database may time out. But anyway, let's move on because we should hopefully only have milliseconds going on here. Bob is waiting. Alice goes ahead. She gets the balance of her account. She reaches in and changes the joint account to 9,000. She then updates her account and then hits commit. Her transaction is over, and that means any lock that she was applying is now unlocked. Bob will now get that message back. The balance is 9,000. He's allowed to continue, get his balance. He can subtract 1,000 from that. We're down to 8,000 as we should be. We update and we commit his changes. The thing is, pessimistic locking is great for Alice, but not necessarily so great for Bob. And if you always do pessimistic locking, you may end up with a lot of read errors or a lot of people having to wait. And although with our situation we know there's a conflict, there's a lot of cases where transactions aren't really conflicting because we're reading multiple pieces of data. We're not always changing everything. So one option with some database systems is to allow what's called optimistic locking, which means Bob would be allowed to read from the table while the transaction is going on because we are optimistic that there won't be a conflict. So we begin with the same situation. Alice and Bob both start. Alice starts her transaction and reads the joint account balance. Bob tries, but where he was refused a moment ago with pessimistic locking, he's going to be allowed to right now. And we'll both continue. Alice will read hers, Bob will read his. Alice will change the joint account down by 9,000. Now, here's the difference. Bob will try and update that too. He thinks he's going to update it from 10,000 to 9,000. What's going to happen with optimistic locking is the database will immediately realize that the contents of this row has changed since he read it, and it's going to actually issue an error. It'll detect that there was a dirty read, and this transaction can't go any further because it doesn't know how to handle that conflict. In most cases, it would just roll back to the beginning of the transaction. Bob would get some kind of error that the application would need to deal with. Alice can continue on because her transaction hasn't thrown any kind of issue, and she can commit with her changes in place. Now, when you're working with locking, both pessimistic and optimistic, this is one of the areas where it's implemented a little differently across database management systems, although the principles are the same. Now, with some DBMS, you have specific keywords to explicitly lock data that you're accessing. With others, there's default behavior, what's called the default isolation level of a database, meaning do we naturally do pessimistic locking or optimistic locking? Or perhaps something in between. We will lock any inserts and updates in a transaction until the commit, but not the selects, just the basic reads. So take a look at your chosen database management system when it comes time to do this.